In this lecture, we're going to review the camera equations, and these are really the basis for the basis for the ISET simulation code and how it is we implement the different functions. So the first thing to remember is that the transfer from photons at the detector surface, this is the irradiance at the sensor surface, to the number of electrons is a linear relationship. And that's what's shown here. And that's true for both CCD and CMOS. This is basic physics of silicon absorptions. There's always a compliance range so that it gets down to 0, or in the Poisson level down here, absorption rates down here, or it saturates up here. But over most of the range, it's basically a linear transfer function. So we can express that in terms of the irradiance at the sensor. So the irradiance at the sensor, which has units of photons per second per nanometer per square meter, times the silicon spectral responsivity times something about the filters. And usually we'll lump in a number. There are a number of filters: the color filter array, sometimes there's an anti-aliasing filter, the lens, and so forth. But they're all the filter and media that get lumped into here. And so the photons are all producted together like this at each wavelength, and then we sum across the different wavelengths. We will integrate for some amount of time, t, that's the integration time, and from the last lecture you'll remember that we have geometric factors that we have to account for, like the shape of the pixel and its position and the microlens and so forth, and we'll lump all of those into an effective pixel cross-section, which also has units of square meters. So what we're counting when we multiply all these things together and add up across wavelengths is how many electrons will be captured in the pixel that we're measuring. And down at the bottom I've got a little units check, so that when you multiply all these together you can see that the product of the units on the right is equal to electrons on the left. In the case of computation, we usually express the electrons in each color channel, shown over here as a vector, and we usually express the computation as a matrix tableau, where we've got the input field as the irradiance, and it's multiplied by the photodiode quantum efficiency, the combined filters, that's at each wavelength. We product those two together. We put this in as a tall vector, and we multiply it through this matrix in order to estimate the number of electrons that we expect in each of the different channels. This dimension here represents each of the different wavelengths, so that this vector interproducted with the row vector here gives you the same equation that we looked at the back in the previous slide. The same equation that gives you the same equation that we looked at in the previous slide, except in discrete form, in the digital form, rather than the continuous integral. It's, for many purposes in computing, it's useful to separate the irradiance into the different physical factors that give rise to the irradiance. In this particular case, I've separated the irradiance into the illumination that's falling on some location within a scene times the surface reflectance at that point in the scene. And we can think of it, it's nice for manipulating in a computer graphics like way the irradiance function by separating it in terms of the surface reflectance of the object and the spectral power distribution of the illumination that's falling onto the object. Trace how a scene might start out as a spectral radiance and become the electrons in your sensor, in the different pixels in the sensor. And this is a little picture that you might imagine sitting on your display screen over here. It's about 1.2 meters from you, and in this simulation, and only 10 degrees across, so it's pretty small. 10 degrees is about the width of your fist at arm's length. This is the number of samples we have, some more description of it over here. And backing this picture in the data inside of the ISET simulation, we have for each pixel some description of the scene illuminant in Q for quanta, or photons, quanta per second per nanometer per square meter. Some fraction of those reflected towards the sensor, towards the camera, and that's the reflectance over here. And the radiance, therefore, headed from this scene towards the camera is represented again in photons per second per steradian per nanometer per square meter. That's what's represented over here, and that's the light the seen radiance headed towards the camera. We can calculate what happens when that radiance arrives at the aperture of the camera and makes it down into the sensor, and that's what we call the optical image, and that's the irradiance at the optical image. And we can do that for different types of F numbers, different types of optics for the fractional limited case, and for different sizes of pixels. That's another option we have. And so if the F number is 2, then the total number of photons that would be arriving would be this very large number, but the total number of photons per square micron in a 10 millisecond interval would only be 152. So there's not a lot of photons there in a single square micron if it's a short exposure duration. Obviously it scales with T, the exposure duration, and it scales with the surface area. If you have a 2 micron pixel on a side, then it's going to be 4 times this amount. If you go to 100 milliseconds, it's 10 times this amount. We can also calculate for this F number what the contrast to noise ratio is. That's to say, what does the mean look like divided by the standard deviation of the noise, of the photon noise, and we put that in a log scale. And for an F number of 2, we've got a fair number of photons, and the contrast to noise ratio is about more than 20 decibels. So that's about a factor of 10. If we, that's again for a 10 millisecond capture and 1 square micron. As we change the F number and we increase it, the contrast to noise goes down and down, so that by the time we're at an F number of 8, and an F number of 8, we have a pretty low level. The human visual system has a sensitivity, and I'll describe this later in the class, that was worked out by Feng Zhao and Joyce Farrell to be, you can see that noise, that level of noise in a capture, if it's lower than 30 dB. That's the limit of the visual sensitivity. So with just a simple calculation like this, we can learn a lot. The irradiance plotted as a function of wavelength is shown over here in this picture. So now we're going to review the architectures of different types of pixels, and then try to make a summary of how the different noise properties of these pixels might influence what pictures look like. Classically, in the way back 25 years ago, the initial attempts to make pixels were just to make passive pixel sensors. There would be a little capacitor, you trap the charge over here, and then there would be a simple switch, and you'd close the switch and you'd kind of wait for the charge to dribble down the output line to get to the place where you would ADC it, you would convert it to a digital signal at the output. And this is kind of a weak form of CCDs. The charge is collected, but instead of moving it tightly and sharply down to the output, you kind of close a switch and wait for the charge to dribble. And those never really did very well. Those are called passive pixel sensors, and really we needed to do better. And then in the early to mid 90s, a new idea emerged from a number of places, but one of them was Eric Fossum, who was down at JPL at the time, and now he's at Dartmouth. And the idea there was that, well, okay, you collect over here, but instead of just waiting passively for these, when you close the switch, wait passively, let's put a buffer in the line. Buffer is basically like a unity gain amplifier, so that instead of waiting for the electrons to dribble down, we're going to just get them down there under some power. And of course, when you put a device in, it can have its own characteristics and noise. And the trick in making an active pixel sensor is to build a set of circuitry for buffering and for resetting and so forth that doesn't add unwanted noise, unwanted characteristics. And that would be called an active pixel sensor. And that technology, that term, is what's used for almost everything that is in your pocket these days on cell phones. There's another notion that we had here, and some others implemented as well, in which, never mind moving the electrons down, suppose you could actually put an analog to digital converter in here and actually turn this into a digital number. In that case, you can move this down the line like reading out memories, super fast. And in fact, you can make super fast sensors, megahertz readouts. if you liked. And but the problem then would be to put an entire analog to digital converter into here, and that was something that Boyd Fowler, Abbas, Dave Yang, a number of others in the group here worked on the architectures for and succeeded. But it ended up not taking off in the market, and I'll tell you stories about that later. So let's go back to the conventional one. Here's a picture of Eric Fossum, and here's a CMOS pixel circuit. This is a 3 transistor circuit for an active pixel sensor, and the concepts will be familiar to you, and you know the circuit diagrams always look a little intimidating to a guy like me, but off we go. Nakamura at Olympus also had these ideas. Eric had these ideas at JPL and started Photobit, which ultimately got purchased. But here we go. So light falls on the pixel, and you can see the light over here, and uses the photoelectric effect that we have been describing to kick loose some electrons. Those electrons are captured, and now we need to buffer on out the signal. So here's a source follower, the buffer, and so there's a voltage over here and a voltage over here, and when the row is selected and the column is selected, the buffer will move this stuff out. Now, not everything always gets moved out, and before you start accumulating, you also need to clear out any residual charge. So the whole point of the circuit is to build it in such a way that you can first reset, and that's what this is, a reset transistor, so that when this transistor operates, it clears out any unwanted charge, and then as the charge accumulates, this is the read transistor. When it switches, it turns on this source follower that puts the voltage out for this row and column when this line is selected. And so there you have your 3 basic transistors that are moving the data from here. And the columns are tied together, and one row is selected at a time. You read these things out in series. So what are the kinds of noise that we would see? And there are various little scripts that I have to help you see these different noise types and to visualize their effects on the camera performance. So the first is that the capture of the electrons themselves from the photons that are incident in the irradiance, that's a random variable, and that's sometimes called shot noise. It arises partly because the photons themselves are variable, and partly because the likelihood, the chance that a photon is converted to an electron, it has a little bit of randomness to it as well. And at very low levels of light, really low levels where you'd have pretty lousy pictures, when you have a mean number of electrons of 1, shown over here in this curve, you'll have a distribution of the electron count that's a Poisson distribution, and 4, here's a distribution shown over here, and 10 shown over here. And you can see that as the numbers get bigger, by the time you get out to about 20, the curve actually looks, or 10 even, but definitely by 20, 40, 50, the curve looks pretty much Gaussian. And here is the formula for the Poisson distribution. It's not Gaussian because you don't get negative, for low values you don't get negative numbers, and the Gaussian has its own properties, and it's a fundamental distribution. For low light levels, the shot noise is Poisson. So what does that look like? Well, you know, we use a simple linear calculation. We can get a no noise distribution. But then if you say what the mean level is, so that we know how many photons are absorbed at every one of the sensors and every one of the pixels in a sensor, we can add the appropriate amount of Poisson noise. And for a dark image, when we have relatively few number of photons per pixel, you can see that we'd get noise that just looks uniform across the image, spatially. Well, here the signal to noise ratio is worse. Here it's a brighter part of the image. The signal to noise ratio is a little bit better, but you can see the noise everywhere through the image. The question of how visible this noise is another interesting question, and that's something that Feng Xiao and Joyce took on. Basically, when you get 1,000 photons incident at the pixel, the noise variance, the standard deviation at that point is 30. Because the square root of 1,000 is 30, and so 1,000 divided by 30 is the signal to noise, and you can't really see stuff that has that high a signal to noise. But if it's only 100 or 200, you can see some of the noise, and that's something that you have to measure with perception experiments. So there are, that noise, that original noise, is just the shot noise, and nothing you can do about that. There's nothing you can do about the circuit designed to get rid of this noise. This noise is just intrinsic to the variance of light. When you start converting it and start using the circuit, well, there are imperfections in the circuit that can add to that noise. So one of them is called the dark voltage. The dark voltage refers to the fact that once you start up the circuit, there's a certain amount of leakage, either of electrons in or electrons out, that takes place over time. How many electrons come in depends on time, and it's always a random number. So the first stage of absorptions, just from the light, you get some fraction. The electrons are proportional to some amount of the light, and then over time the dark current leaks in by a certain amount of time. And then the act of reading and resetting, remember this business about resetting. After we take a shot, we turn this resistor on and we reset the charge over here, and then when we read out, we turn this resistor on to go start moving the charges through this pathway over here. Well, reading and resetting also add some amount of noise. There can be stray electrons that get in and out of our pathway, and so these are all of these terms are part of the pixel level noise that that we put into the full noise model, so that by the time you start with the incident number of photons, you end up with a voltage that has all these different noise terms grouped into them, and that's what the simulation looks like. So just a little bit more to say, the dark noise, and there's also a sense of just noise. So next, let me give you a sense of some of the complexity. Let me review some of the complexity and actually some of the auxiliary parts, anti-aliasing, infrared filters, color filter array types, that are part of building up from these original sensor into the full camera system. I really, in this section, want to give you a sense of all the different parts that we've already gone through and that we're still going to go through before we get something that feels like a good working camera. So we went through so many different decisions already, kind of implicitly, about the pixel properties, like its height and width, what fraction of the pixel is occupied by the photodetector as opposed to the vias and circuitry. We looked at the noise properties. We didn't really talk about, but there's a sense in which this phrase conversion gain refers to the amount of voltage that we get per electron that comes out, and that has to do with the circuitry, the transistors, and the buffering gain and so forth. There's only so many electrons that you can hold in a pixel, so that limits how many electrons. That's sometimes called the well capacity, but here I represent it as by converting the electrons to voltage. You can also call it the voltage swing of the pixel, and these can be a volt or a little less. It depends on the size of the pixel, how big the capacitors are. There are the array properties, things like the number of pixels and their spacing and the non-uniformities and the gain and so forth. We now are going to start looking at some of the color properties, and we've already been looking at some of the properties pertaining to ADCs, and of course there are things to worry about like the pixel optics themselves, the micro lenses. So lots of different parts. But one of the simpler and more important and crucial parts to think about for designing a camera is pertains to the question of anti-aliasing. And also related to this, because they're often handled by the same part, is infrared blocking filter. So this is an anti-aliasing and infrared blocking filter, and that's usually placed just in front of the sensor surface, and it does the two things that its name implies. First off, when you capture photons from the scene into a camera that's designed for consumer photography, you want that camera to be seeing the same photons that the human eye would see. Well, the human eye does not see infrared light very well. It hardly sees it at all, and so therefore you don't want the infrared photons say from 700 and on up to the 1100 nanometer band gap, to be influencing the sensor, because the sensor would be responding to stuff that you would not be responding to. So we put infrared blocking filters in order to make the sensor a little bit more like the human eye. The other thing that we always have to worry about is the match between the number of spatial samples in the pixels with how many spatial samples we have in the pixels compared to the quality of the image that's produced by the optics. And if the optics is producing an extremely sharp image, but we have a low sampling rate on the sensor, then we will get into all kinds of trouble with a phenomenon called aliasing. And there's a script, sensor alias, that that you should run through, and that's a video online, and that illustrates what the problem looks like in terms of sensor aliasing when you've critically undersampled with the sensor sampling the quality of the optics. The optics produces a high resolution image and the sensors sample coarsely, and that's described in the tutorial in some detail, and you can quantify it. And so so this filter is designed to prevent that kind of a problem. So there are really two types of anti-aliasing filters that people use. They put the IR blocking in here because it's convenient. You don't want to have two separate filters. The anti-aliasing filters can be based either on this particular kind of interesting birefringent material, lithium niobate, and it's commonly used here in this case. I should say that the anti-aliasing filter sits up here at the very top. And the idea of these anti-aliasing filters is like this. We want to make sure that we blur the image in a couple of ways. We want to make sure that we blur it so that all of these 4 pixels in the sensor, the red, 2 greens, and blue, are seeing the same point of light in the original scene. So if this guy and this guy, the red and green, see different points of light, then when we do our image processing subsequently, we will have trouble, because this will be reporting on the red of one point and this will be the green of another point, and it'll be very hard to combine them. So we want to make sure that our blur circle at least includes these 4 pixels. And if we don't, then we end up having these kinds of classical aliasing problems in which the image comes in at a very high rate, varies, but you're only sampling coarsely like this. And so even though the original image is this high spatial frequency, the image that you get in response is this low spatial frequency, and that's called aliasing, and that's what's described in this and the other ICIT script that illustrates the phenomenon of aliasing and quantifies it for you. So this is what it looks like, aliasing looks like when things are undersampled. In fact, and for a camera, when you have red, green, blue kinds of pixels, as you use a sweep frequency that goes from low to higher spatial frequencies, the patterns that emerge at the high frequency are actually chromatic patterns, not the classic achromatic patterns that you're used to seeing in aliasing demonstrations or in audio demonstrations. That because of the Bayer array, they come on out as chromatic patterns like this. These are just little examples of the trade-off of kind of the cost that you're paying for using an anti-alias filter. This is a little bit of an image over here where you can see this pattern here has some aliasing in it. It's a very high frequency pattern in this image, and the optics were good, and you end up with these kind of funny lines going the wrong way over here. Well, they're not in the air conditioner. Those are aliasing artifacts. If you put the anti-aliasing filter in front of the sensor, you can see those are gone. The image as a whole is blurrier, but the artifacts are removed. And so different people prefer different looks, and mostly cameras are now such high resolution that they're shipped with anti-aliasing filters, and even when they're anti-aliased, the images still look very good and sharp. So the birefringent filters, which are used for blurring, birefringence refers to the fact that when a ray is incident on the light, I'm sorry, on a birefringent filter, it'll divide into two directions. One is called the ordinary ray that sort of carries on in the way an ordinary ray might through a material. And then it also produces a second ray called the extraordinary ray. They have different polarizations and they head out in slightly different directions. So now when you look at the output of this filter, you'll have two spots, not one. You'll have this intensity arising from the ordinary ray transmission and a second one from the extraordinary array. So if you put, and you can see that in this picture right here, you can see that here's a laser beam going through a calcite crystal, and you can see that there are two rays that come out. They're split like this and this. And if you just put the crystal in front of some text, you can see that it's divided. It's divided the text underneath into mirrored copies, little shadowed copies of it, the ordinary and extraordinary rays. So we can simulate that if we have a scene of just a set of points, and we go calculate the image. One of the anti-aliasing filters you can just turn on in the optical image calculation. An ISET is a birefringent filter, and that filter, they're designed, I've shown them to you with an ordinary ray and an extraordinary ray, but if you put two of them in, then you can take this ordinary ray and split it again, and the extraordinary ray and split it again, and you get a little 2x2. And you can see why this might be interesting to people who make sensors. These are interesting because you've got a red, two greens, and a blue pixel underneath. So this pretty much guarantees that a single ray will be divided over a superpixel in a bare mosaic. And so this is the input was a single spot. You put it through the birefringent filter, and you get a little 2x2 like that that'll cover the 4 pixels in a bare in a sensor that's got a bare mosaic. Another thing to do is, just never mind all the fanciness. Just go get me something that's a little diffuser, like a quartz diffuser or something that just blurs the image. So instead of being all that fancy with these 4 little dots and the birefringents and stuff, just blur that bad boy. So okay, so you can say how sharp it's going to be, and the other type of anti-aliasing that we've implemented is just a little blur filter. In this case, the full width, half max of the blur circle is 2 microns, and that might also be good enough to. So we can check how much of a difference it makes to use these two different types of filters, the blur filter or the birefringent filter with the 4 spots. And you can do this through simulation by literally just taking that point array and going and calculating at the sensor what happens if you use the diffuser. And here are all the spots, and you can see various little pixels are indicated. The different color types are indicated here, and that's the kind of picture you would get, the kind of sensor responses you would get with the diffuser. And this is with the birefringent, and I'll just flip back and forth between the two, and you can see that all things that the difference between the diffuser and the birefringent filters at the level of the sensors are really extremely small. So you could choose based on price or weight or availability and so forth, and it really wouldn't have a big effect in this particular instance for this particular optics and this particular sensor.